Black holes are not what you think they are. They are not cosmic vacuum cleaners sucking everything nearby. They are not dark spheres floating in space. They are not even holes. Every single thing you have ever been told about black holes, every image you have seen, every analogy you have heard is fundamentally wrong. And when you understand what black holes actually are, your entire conception of space, time, and reality itself will be shattered beyond repair. Ask anyone what a black hole is, and they will tell you it is a region of space where gravity is so strong that nothing can escape, not even light. This sounds like a reasonable description. It is what textbooks say, it is what science communicators repeat, it is what everyone believes, and it is completely wrong. Not wrong in some minor technical detail, wrong at the most fundamental conceptual level. Black holes are not regions of space with strong gravity. They are not objects in space. They are not things that exist in the way you think things exist. Understanding what black holes actually are requires abandoning almost every intuition you have about objects, space, time, and causality. Let me start by telling you what a black hole is not. A black hole is not a hole. There is no tunnel through space. There is no void or gap or absence. The word hole is perhaps the most misleading term in all of physics. It makes you think of something missing, a cavity, an emptiness. A black hole is not empty. It is the opposite of empty. It is a region where space-time itself has been curved to its maximum possible extent. It is not nothing. It is everything compressed into the smallest possible volume. A black hole is not black. Black means absorbing light without reflecting it. A perfect black surface absorbs all light that hits it. But a black hole does not absorb light in this sense. Light that approaches a black hole does not hit a surface and get absorbed. Light follows geodesics, paths through curved space-time. Near a black hole, space-time is curved so extremely that the geodesics that light follows lead inward toward the singularity. Light does not choose to go in. Light has no choice. The geometry of space-time itself forces all future directed paths to lead inward once you cross the event horizon. A black hole is not a cosmic vacuum cleaner. This is perhaps the most common misconception. People imagine that black holes suck in everything nearby like a drain or a vacuum. This is wrong. Black holes attract matter gravitationally exactly like any other mass. If you replace the sun with a black hole of the same mass, Earth's orbit would not change at all. We would not get sucked in. We would continue orbiting exactly as we do now. The only difference is we would be very cold because the black hole would not emit light like the sun does. Black holes only capture things that get too close. The distance at which capture becomes inevitable is the event horizon. Outside the event horizon, you can orbit a black hole safely forever. Inside the event horizon, you cannot escape, but there is no sucking, no pulling, no vacuum effect, just gravity behaving according to Einstein's equations. A black hole is not a three-dimensional object with an interior you could map. This is where things get truly strange. When you think about a black hole, you probably picture a sphere in space. The event horizon is the surface of the sphere. Inside the sphere is the interior of the black hole, leading to the singularity at the center. This picture is wrong in a subtle but profound way. The event horizon is not a place in space, it is a place in space-time. It is not a surface you could touch or measure. It is a boundary in the geometry of space-time itself. The event horizon is the set of points from which light rays heading outward never escape to infinity. It is a one-way membrane in space-time, not a physical membrane in space. Here is the key insight that everyone gets wrong. Once you cross the event horizon, the direction toward the singularity is not a direction in space, it is a direction in time. Inside the event horizon, the singularity is not a place you could avoid by turning around. The singularity is in your future. Moving towards the singularity is not like moving toward a location. It is like moving toward next Tuesday. You cannot avoid next Tuesday by turning around or changing direction. It is in your future, and the future happens whether you like it or not. This is what general relativity actually tells us about black hole interiors. The radial coordinate, the direction that points toward the center, becomes time-like inside the event horizon. The time coordinate becomes space-like. The singularity at the center is not a point in space. It is a moment in time. It is the final moment. When you cross the horizon, you have a certain amount of proper time before you hit the singularity, typically seconds to minutes depending on the black hole's mass. During that time, you can move around inside the horizon, change direction, do whatever you want, but you cannot avoid the singularity any more than you can avoid tomorrow. People imagine the singularity as a tiny point of infinite density at the center of the black hole. This picture is wrong. The singularity is not at the center, it is in the future. All of space inside the horizon hits the singularity simultaneously, not as a spatial meeting point, but as a temporal ending point. The singularity is when the interior ends, not where it ends. Now let me tell you what a black hole actually is. A black hole is a region of space-time where the curvature becomes so extreme that the causal structure inverts. Outside the horizon, time is time and space is space. You can stay at a fixed location in space and let time pass. Inside the horizon, this becomes impossible. The direction that was radially inward becomes a time direction. You cannot stay at a fixed radius any more than you can stop time from passing. You fall towards smaller radii, not because something is pulling you, but because moving towards smaller radii is what forward time evolution means inside the horizon. This is not a metaphor. The mathematics of general relativity makes this precise. The Schwarzschild metric, the simplest solution describing a non-rotating black hole, has a coordinate singularity at the event horizon. When you transform to coordinates that are smooth at the horizon, like Kruskal-Szekeres coordinates or Eddington-Finkelstein coordinates, you see clearly that the time and space coordinates swap their character across the horizon. What this means is shocking. A black hole is not an object in space-time. A black hole is a feature of space-time geometry itself. It is a region where the light cone structure, the set of possible future directions, tilts so far over that all future directions point inward. You do not fall into a black hole because it pulls you. You fall into a black hole because once you cross the horizon, falling is what time means. The event horizon itself is not made of anything. It is not a physical boundary. It is a mathematical surface in space-time, defined by the condition that light rays emitted from it never escape to infinity. As you cross the horizon, you do not encounter anything. There is no barrier, no interface, no transition. If the black hole is large enough, you would not even notice crossing the horizon. You would only notice when you started to feel tidal forces pulling you apart as you approach the singularity. This leads to a profound realization. You cannot see the event horizon from outside. You can infer where it must be from the effects you observe: light and matter disappearing, gravitational lensing, redshift effects. But the horizon itself is not observable from outside. It is not an object in your visual field. It is a boundary in space-time that you can only identify by calculating the causal structure. From the perspective of someone falling in, there is no moment when they cross the horizon and suddenly everything changes. The crossing is smooth. The laws of physics are continuous. An observer falling through the horizon experiences nothing special at that moment. Only later, as tidal forces grow, does the observer realize something terrible is happening, but by then the singularity is unavoidable, not because it is a place they are being pulled toward, but because it is a time they are moving toward, and time moves in only one direction. The singularity itself is another profound misunderstanding. People imagine the singularity as a point of infinite density, infinitely small, infinitely massive per unit volume, all the mass of the black hole compressed into a point. This picture may or may not be accurate, and the reason has to do with quantum mechanics. In classical general relativity, the singularity is indeed a point of infinite curvature where the equations break down. The density and curvature become infinite. All the matter that formed the black hole and all the matter that has fallen in since is compressed to zero volume with infinite density. This is what the classical equations say. But everyone knows this cannot be right. Quantum mechanics must become important at sufficiently small scales. The Planck length, about 10 to the negative 35 meters, is the scale at which quantum gravity effects dominate. We do not have a complete theory of quantum gravity. We do not know what replaces the classical singularity when quantum effects are included. String theory suggests the singularity might be replaced by a region of highly excited strings. Loop quantum gravity suggests space-time itself becomes discrete at the Planck scale, and the collapse halts at a finite density. Other theories propose different possibilities, but all agree that the infinite density singularity of classical general relativity is not the final answer. What is certain is that the singularity represents a boundary of our physical theories. Where the singularity is in classical general relativity, something unknown happens. But this does not change the fundamental fact. For any observer who crosses the horizon, the singularity, whatever it really is, lies in their future, and they will reach it. The quantum resolution of the singularity does not save you. It just means you hit something different than infinite density. You still hit it. You still end. Now let me address the most persistent and deeply wrong misconception about black holes, that they are eternal, unchanging objects that last forever. Black holes evaporate. This is not speculation. This is a robust prediction of quantum field theory in curved space-time discovered by Stephen Hawking in 1974. Black holes emit radiation. They have a temperature, and they slowly lose mass by radiating away energy until they eventually disappear completely. Hawking radiation arises from quantum effects near the event horizon. The vacuum of empty space is not truly empty in quantum mechanics. It seethes with virtual particle pairs that pop into existence, briefly exist, and then annihilate back into nothing. Near the horizon of a black hole, one member of a virtual pair can fall into the black hole while the other escapes to infinity. The escaped particle is real Hawking radiation. The particle that fell in has negative energy from the perspective of the exterior spacetime, and it reduces the mass of the black hole. The temperature of the Hawking radiation is inversely proportional to the mass of the black hole. Small black holes are hot, large black holes are cold. A solar mass black hole has a temperature of about 60 nanokelvins, far colder than the cosmic microwave background. Such a black hole absorbs more energy from the background than it radiates. It grows rather than shrinking. But a primordial black hole with the mass of a mountain would have a temperature of billions of degrees and would evaporate rapidly in a shower of high-energy particles. As a black hole radiates, it loses mass. As it loses mass, its temperature increases. As temperature increases, radiation rate increases. This creates a runaway process. The evaporation accelerates. In the final moments, the black hole evaporates explosively in a burst of high-energy radiation. The time scale for complete evaporation is enormous for stellar mass black holes. A solar mass black hole takes about 10 to the 67 years to evaporate completely. But the point is, they do evaporate. Black holes are not eternal. They are temporary structures that form, persist for a time, and then disappear. This evaporation creates one of the deepest problems in theoretical physics. The black hole information paradox. When matter falls into a black hole, it carries information. The quantum state of the matter encodes information about its properties. That information seems to disappear behind the event horizon. When the black hole eventually evaporates completely through Hawking radiation, where did the information go? Hawking radiation, as originally calculated, is purely thermal. Thermal radiation contains no information. It is random. So, if a black hole evaporates into thermal radiation, the information about what fell in seems to be destroyed. But quantum mechanics says information cannot be destroyed. Unitarity, the preservation of information, is a fundamental principle of quantum mechanics. If information is destroyed, quantum mechanics breaks down. This paradox has driven theoretical physics for decades. The resolution, which is still being worked out in detail, involves the holographic principle and the realization that information is not actually lost. The information that fell into the black hole is encoded on the event horizon in a scrambled form. As the black hole evaporates, this information is gradually released in subtle correlations in the Hawking radiation. The radiation is not purely thermal. It contains information encoded in patterns too complex to easily detect, but the information is there. This connects to another profound misconception: the idea that black holes have well-defined interiors independent of observers. The black hole complementarity principle, developed by Leonard, Susskind, and others, resolves the information paradox by recognizing that different observers have fundamentally different but equally valid descriptions of what happens to infalling matter. An observer falling into the black hole experiences crossing the horizon smoothly and hitting the singularity. Nothing special happens at the horizon from their perspective. But an observer far outside the black hole never sees anything cross the horizon. Due to gravitational time dilation and redshift, infalling objects appear to slow down and freeze at the horizon, their light becoming increasingly redshifted until they fade from view. From the outside perspective, the information about the infalling matter remains on or near the horizon forever and is eventually released in Hawking radiation as the black hole evaporates. Both descriptions are correct. They do not contradict, because no single observer can verify both. The infalling observer cannot communicate their experience to the outside after crossing the horizon. The outside observer cannot verify what the infalling observer experienced. Quantum mechanics allows both descriptions to be true simultaneously because they involve complementary observables that cannot be measured together. This is deeply weird. It means the black hole interior may not be an objective feature of reality. It may be observer dependent. The interior exists for someone who falls in. The interior does not exist in the same way for someone who stays outside. Both descriptions are complete and correct within their domains of applicability. Another major misconception involves the size of black holes. People hear that stellar mass black holes are only a few kilometers across and imagine they are small. But this confuses the event horizon radius with the size of the interior. The event horizon radius of a black hole is proportional to its mass. The Schwarzschild radius is about 3 kilometers per solar mass. So a 10 solar mass black hole has an event horizon radius of about 30 kilometers. That is the size as measured from outside. But what about the interior volume? This question has no simple answer because the interior of a black hole is a dynamical space-time region. The volume inside the horizon grows with time. From the moment a black hole forms, its interior volume increases. This is not because space is being added from outside. This is because the interior space-time region is expanding. The geometry inside the horizon is such that spatial volume increases as you move forward in time. For a large black hole, the volume inside the horizon can be enormous, much larger than the volume of a sphere, with radius equal to the Schwarzschild radius. The classical interior volume can grow without bound as time passes. An observer falling in may experience vast amounts of space inside the horizon before hitting the singularity, far more space than you would naively calculate from the horizon radius. Supermassive black holes at the centers of galaxies present another misconception. These black holes have masses of millions or billions of times the sun's mass. People imagine them as monstrous objects tearing through their galaxies, destroying everything. But the average density of a supermassive black hole is extremely low. The volume inside a black hole's horizon scales as the cube of the mass. The mass scales linearly, so the average density scales as mass divided by volume, which is inversely proportional to mass squared. Larger black holes have lower average density. A supermassive black hole with 1 billion solar masses has an average density less than water, less than air even. You could be inside the event horizon of a supermassive black hole and not immediately notice anything unusual except that you are doomed to reach the singularity. This does not mean supermassive black holes are not dangerous. Once inside the horizon, you cannot escape. Tidal forces will eventually tear you apart as you approach the singularity. But the common image of black holes as infinitely dense points is misleading. The density at the singularity may be infinite, but the average density inside the horizon is not. Rotating black holes add another layer of complexity. The Kerr solution describes a rotating black hole, and it has even stranger properties than a non-rotating Schwarzschild black hole. A rotating black hole has an ergosphere outside the event horizon where space-time itself is dragged around in the direction of rotation. Inside the ergosphere, you cannot remain stationary. You are forced to rotate with the black hole whether you fire your engines or not, because space-time itself is rotating. The Kerr black hole has two event horizons, an outer and an inner horizon. Between them is a region where the singularity is not inevitable. In principle, you could cross the outer horizon, enter the region between the horizons, and if you aimed correctly, exit through the inner horizon into a strange region of space-time that might connect to another universe or another part of our universe. This sounds exciting until you realize the inner horizon is unstable. Any perturbation, including your own presence, destroys the inner horizon region. The idealized Kerr solution is unstable to perturbations. Real rotating black holes do not maintain the clean structure needed for these exotic regions to exist. The inner horizon becomes a chaotic boundary where quantum effects and classical instabilities dominate. You do not find a passage to another universe. You find a maelstrom that destroys you. Inside the inner horizon of the idealized Kerr solution is a ring singularity rather than a point singularity. The singularity has the topology of a circle. In principle, you could pass through the ring without hitting it. What lies beyond is unknown because the classical equations give ambiguous or paradoxical results. This is another signal that quantum gravity is needed to understand what really happens. The event horizon also has thermodynamic properties that are deeply misunderstood. A black hole has entropy proportional to the area of its event horizon. This is the Bekenstein-Hawking entropy formula. Entropy is a measure of the number of microscopic states that give rise to the same macroscopic configuration. The fact that black hole entropy depends on surface area rather than volume is one of the deepest clues we have about the nature of quantum gravity. The holographic principle emerges from this observation. The maximum entropy that can be contained in a region of space is proportional to the surface area of the region measured in Planck units, not the volume. This suggests that the three-dimensional interior of space might be a holographic projection of information stored on a two-dimensional boundary. Black holes are the key evidence for this principle. What this means is that the information content of a black hole is not stored in its interior volume. It is stored on the event horizon. The horizon area in Planck units tells you how many bits of information the black hole contains. This is why information does not get lost when matter falls in. The information is encoded on the horizon and later released in Hawking radiation. Black holes are therefore not just weird objects, they are windows into the deepest structure of space-time and quantum mechanics. They are laboratories where quantum mechanics and gravity meet, where space-time curvature reaches its limits, where information and entropy reveal the holographic nature of reality. Everything you thought you knew about black holes, every visualization, every analogy, every simplified explanation, misses these profound truths. Black holes are not holes, not vacuum cleaners, not eternal, not infinitely dense throughout, not purely classical objects that can be understood without quantum mechanics. Black holes are regions where time and space exchange roles, where the singularity is a moment rather than a place, where entropy is measured by surface area, where information is preserved but scrambled beyond recognition, where observers have fundamentally different but equally valid descriptions of reality, where the distinction between interior and exterior is observer-dependent. They are not things in the universe. They are features of the universe itself, scars in space-time, boundaries between the possible and the impossible, regions where reality reveals its deepest and strangest properties. And understanding them correctly requires abandoning almost every intuition you have built up from living in the macroscopic classical world. Black holes do not play by the rules you know. They play by the rules of quantum gravity, and those rules are far stranger than anything science fiction has ever imagined.